analog to digital converter types. Majorly, we'll be seeing about CounterType ADC, successive approximation register type ADC, flash ADC, and dual slope integrating ADC. So this video is a quick revision of the circuits and the important equations of various ADCs. Okay, so I have done a detailed video on analog to digital conversion process. I'll be linking that in the description box. Okay, so the function of an ADC means analog to digital converter. So it is used for converting an analog signal to its digital version or digital approximation. Okay, and the analog to digital converter or ADC accept analog signals and they'll be converting the signal to digital. And the two major operations performed in order to do this process is sampling and quantizing. So by sampling, so the ADC will first sample the signal and then quantize the signal in order to have the digital representation of the corresponding analog signal. Okay, so that is the brief about analog to digital conversion process. I'm telling it again. I'll be linking that video in description. If you want to know the detailed explanation about ADC or analog to digital conversion, please do watch that video. Okay, next we are going to see about the major type of ADC. How is its structure looking like? What is the major equations? Because in a lot of competitive examinations, you have to answer questions from this area. So these are very important. Sometimes comparison of these ADCs, this type of questions can also come. Okay, so if you are preparing for any competitive examinations, I request you to watch this video till the end. Okay, so we are going to see about these type of ADC. There are other type of ADCs also. There is folding type ADC, there is sigma delta ADC. There are a lot of variants of ADCs. In this one type itself, there are sub versions, but the major types are these four. Okay, counter type, successive approximation, flash ADC, and dual slope integrating ADC. This type of ADC that we are going to see is a counter type ADC. This is a very simple structure of ADC. So this is the structure of a counter type ADC. It consists of a counter, a DAC, there is a control logic, and there is a clock signal generator, and there is a comparator. So in ADCs, you can always find a comparator, which is used for comparing the voltage which we produce, its digital approximation. Then we have to compare with the given voltage. Only when this approximation is right, we'll take that digital representation, right? Okay, anyway, we'll see about the very brief working of this counter type ADC. For a counter type ADC, we'll start from this control logic. So the control logic on reception of the start signal will send a signal to the counter in order to it resets the counter and also starts the counter, and it also gives a signal to the clock signal generator, which is used for providing the clock to the counter. The counter will increment by 1 on every clock cycle, and the output of this counter is given to the DAC. Now the purpose of a DAC means it is used for the counter output is digital version. So in order to convert that to analog version, we use a digital to analog converter or a DAC, and this voltage will be compared with the given input voltage, which we actually want to that is for any voltage we want to produce a digital output means that is Vi. Okay, so we will compare these two. If the comparison is, that is if Vi is greater than Va, means your output of the comparator is 1, and if Vi is less than or equal to Va, then the output is 0. Okay, and when the output of the comparator is 0, means this is also connected to the control logic. The control logic will produce a signal to disable the clock, and also it stops the counter, and whatever digital output is at the counter, it will be taken as our final digital representation of the given signal Vi. This is the simple working of a counter type ADC, and this is the structure of a counter type ADC. Okay, so in competitive examinations, they won't be asking the structure or its explanation. They will be asking the below given details. Okay, these are very important equations. For a n-bit ADC, the maximum clock pulse required for conversion is 2 raised to n minus 1. Okay, Next one is very, very important. The time of conversion, or TOC, for all ADCs are important. Sometimes directly this equation may be asking, or sometimes problems can come. Okay. So the maximum time required for conversion is 2 raised to n minus 1 into t clock. It is the period of 1 clock. Then the minimum number of clock pulses is at least 1 clock pulse is anywhere required. The average number of clock pulses is 2 raised to n minus 1. Okay. So that is the maximum or the average pulse. Okay. Anyway, the most important equation is this, which is the time of conversion equation is 2 raised to n minus 1 t clock is the maximum time of conversion, or the time of conversion required for a counter-type ADC. The next type of ADC is successive approximation register type ADC. The only difference from the previous counter-type ADC is in the structure. There was a counter here for a counter-type ADC. Here it is a successive approximation register. So it is very easy to remember the structures or the figures. Okay. So this register is a successive approximation type of register, and we are replacing the counter with this in the case of a successive approximation register ADC. That is the difference from the counter-type ADC. Okay. So the working is, again, we'll start from the control logic. The control logic will reset all the bits of the successive approximation register while the conversion is starting, and it enables the clock signal also. That is, it enables the clock signal generation, and it will send a pulse to, or a clock pulse to, the successive approximation register, and the data is updated in the successive approximation register on every clock pulse based on the comparator output. Okay, so that is happening here, and the output of this successive approximation register is given to the DAC. Okay, again the DAC will convert the digital representation back to the analog voltage, and a comparison is done here in the comparator. Okay, it is just like the previous case. When Vi is greater than Va, your output is equal to 1, and when Vi is less than or equal to Va, right, when Vi or the input is less than or equal to Va, your comparator output is 0, and what happens? Again, it will be sending a signal to the control signal, which will stop the conversion, and whatever output is here will be taken as your digital output of this particular, or digital representation of this Vi signal. Okay, so this is happening for a successive approximation register ADC. And if you see the structure or the working of a successive approximation register ADC, it is faster than digital ramp ADC, and the conversion time is independent of the applied voltage. In most of the cases, the conversion time is independent of the applied voltage or the analog voltage, both Vi, and also it is not depending on Va also. And the maximum number of clock pulses is n. For the previous counter-type ADC also, you have to only consider the maximum clock pulses and the time of conversion. That are the most important things. The average clock pulses you don't require actually. Okay. So the maximum number of clock pulses required is n for a n-bit ADC, and the time of conversion is n plus 2 clocks. Okay. Or it is not clock, it is t clock. Okay. This is the time of conversion. For 1 clock period, this is t clock is the clock period into n plus 2. Now for some textbooks, or in some textbooks, this is given as nt clock also. Right. For a n-bit ADC, the time of conversion of a successive approximation register, in some textbooks it is given as nt clock. But in majority of the places it is given as n plus 2 t clock. Why this 2 is coming? Because there is 1 clock pulse for start of conversion and 1 clock pulse for end of conversion. 2 clock pulses are actually used for these two purposes. So n plus 2 t clock is taken as the maximum conversion time, or the time of conversion, or TC. You can call this as TC. Okay, so I would suggest you to follow this equation. The time of conversion for a successive approximation register ADC is n plus 2 t clock. Okay, but just have in mind that there is some textbooks which is following this equation also. Okay, so this is a successive approximation register ADC and is having fixed conversion time. Okay. The next type of ADC that we are going to see is a flash ADC. So out of these ADCs, the fastest one is flash ADC. And this is a structure of a 3-bit flash ADC. Okay, so the 3-bit flash ADC consists of, there is an initial VI, which is an input voltage. There is a reference voltage we apply across the set of voltage divider network. This is actually a voltage divider network of various resistors connected in series, and there is a set of comparators, and the comparators result is given to the parity encoder, which will encode. We know that the encoder will produce a digital output. It will encode the sequence or the output and it will produce a digital output. So this is a 3-bit flash ADC. Now, for the case of a 3-bit flash ADC, the voltage drop across each resistor from bottom to top will be given to the negative terminal of the comparator. So there is comparators. The comparators will be having negative and positive terminal, and these voltages. So here it is V by 8. So here it is 2V by 8. So likewise it will be going V by 8, 2V by 8. Likewise the voltage drop will grow from bottom to top. This is a voltage divider network of various resistors. How the number of resistors varies, we will see in the end. Just consider that this is a resistor connection and it is used as a voltage divider to provide voltage values at the comparators at each level. So there are various levels of comparators or comparison for obtaining each bit. So we'll be applying the reference voltage through this voltage divider network, and the voltage drop across each resistor from bottom to top with respect to the ground will be integer multiples of V by 8. Here there are 8 resistors, 1, 2, 3, 4, 5, 6, 7, 8. So the voltage drop will be integer multiples of V by 8 as we move on each resistors. V by 8, 2V by 8, 3V by 8 likewise. Okay. So it will be moving like that. Here it is V by 8, 2V by 8, 3V by 8 on each negative terminal of various comparators. It will vary. Okay. And Vi or your input voltage is applied to, you can see very clearly, it is applied to the positive terminal of each comparators. Okay. So each comparator will compare the input voltage at various levels based on this reference voltage. Okay, and the comparator output is given to the parity encoder, and the parity encoder will produce, just like any other encoder, to be producing your approximate or digital representation of your signal. Okay, so this type of ADC is also called parallel comparator type ADC or simultaneous converter ADC. Okay, so these are two names given to the ADC. Now we move on to the equation part. So I'm telling it once again. So it consists of a voltage divider network of various resistor connections, and there is a comparator network, and there is a parity encoder unit. Okay, so if you are using an n-bit ADC, then the number of comparators required, it is very important equation. I have seen a lot of question papers asking this question. The number of comparators is equal to 2 raised to n minus 1. Here I am using a 3-bit flash ADC. So 2 raised to 3 minus 1. 2 raised to 3 is 8. 8 minus 1 is 7. How many comparators are there? 1, 2, 3, 4, 5, 6, 7 comparators are there. Okay, so here it is 7. And the general equation is 2 raised to n minus 1. Please note it down. It is very important. The number of resistors for the resistor network or voltage divider network is 2 raised to n. It is 2 raised to 3 here, which is equal to 8. 8 resistors are there, right? So anyway, next is the number of parity encoders required is 1, and it is 2 raised to n is to n type of encoder. Okay, so that is the general equations for a flash ADC, and just know that it is a fastest type of ADC and the complete conversion will be obtained in 1 clock cycle. Okay, so this is the within the given general type of ADCs, flash ADC is the fastest one. Okay, and we are seeing here the structure of a 3-bit flash ADC. I hope it is clear. The next type of ADC that we are going to see is dual slope integrating type of ADC. This is a very important type of ADC when concerning to competitive examinations, because there is a lot of equations and you can expect numerical questions also. Okay, so this ADC is called dual slope integrating type of ADC, and from the name itself it is clear that it is having an integrator. It doesn't have a DAC unit inside the circuit. So this is having low cost and it is slowest. Okay, the flash ADC was the fastest. Comparing to the speed, this is the slowest. Now this is the structure of a dual slope ADC. Here I have included one equation. So till here, okay. So there is an integrator, there is a control logic, there is a counter which will be producing the output here. So here you can find your digital output. There is a comparator and a clock signal generator. Okay. The working is like this. Everything starts with the control logic. Okay, so when a start signal is received, the control logic will reset the counter and will enable the clock signal generator, just like in the previous cases also. And here there is one more duty. It required to connect, there is a switch here. You can see there is a switch here. So it need to connect this switch to the input voltage terminal Vi. So there is a Vi and a minus Vr. So this control logic on receiving the start signal connects the switch to Vi. Okay. And it will start its conversion, and while it is connected, what will happen? The integration will start and the integrator output is connected to the comparator, and one of the outputs of the comparator is connected to the ground. So the comparator compares the output of the integrator, and on every clock cycle the counter will be incremented by 1. And what happens when the counter will reach its maximum count? So this counter will go on incrementing and it will reach the maximum count, and on reaching the maximum count it generates an overflow signal and it sends this overflow signal to the control logic, and the control logic will require an that is, it will receive an alert signal. Now it will stop the counter and it will reset the counter to zeros again, and then it will connect the switch from Vi now to minus Vr, or it is a reference. Okay, so it will connect the switch from Vi to minus Vr on receiving of this overflow signal. Okay, so now the control logic will connect the signal to minus Vr, and again it will start integration. It will be connected, that is, the switch will be connected to minus Vr, and via it is connected to the integrated, right? And at this point what happens is that in the integrator unit, when it is connected to minus Vr, that is when the switch is connected to minus Vr, the integrator will actually remove all the stored charge from the capacitor and make it equal to 0. That will happen actually. So you can make it more clear or clarified while seeing the graph. Okay, so when the switch is connected to minus Vr, the integrator will actually remove all the charges from the, you know that there is a in an integrator there is a capacitor. So the capacitor gets charged and discharged. So when it is connected to minus Vr, discharging actually happens in the capacitor present in the integrator unit. So the charge will get removed and make the charge of the capacitor equal to 0. Now both the inputs of the comparator are at ground. So the capacitor output is, the capacitor charge is all removed. So the output from the comparator is also 0 and the other unit is also grounded for the comparator, right? So when the comparator have both its inputs equal to 0, it will send a signal to the control logic. You can see there's a connection between the comparator and the control logic. So the comparator will send a signal to the control logic to stop its clock signal production. So the clocks and the control logic will again send a signal to to the clock signal generator to alert it to stop the production of clock pulses. Okay, so the clock pulses will get stopped, and at this point the counter, whatever is present at the output of the counter, will be taken as your digital output. So while removing the charge also, the counter will operate. Okay, So don't think that the counter has stopped. It will again operate for the next cycle also. When the switch is for Vi also, when the switch is also for, when the switch is connected for to minus VR also, the counter will start again. Okay, so when the clock signal is stopped, only then the counter will stop and your output will be the representation of your analog signal Bi. Okay, so this is the working of a dual slope integrating type of ADC. So it has two type of integration or two conversion cycles. There is an up conversion and a down conversion. You generally say it like that. So initially the capacitor's charge gets increased, then the capacitor stored charge is removed and it is made as equal to 0. Okay, now let's see the graph of this dual slope integrating. It is also important. So initially it is having a slope of minus Vi by Rc. Since the integration is happening, capacitor is getting charged now since the switch is connected to Vi. When the counter has overflowed and the reset is happened, then the discharge of the capacitor will take place and it will overflow and it will remove all the charges and it will make the charge of the capacitor equal to 0. So you can call this cycle as TU or up conversion cycle. This is down conversion cycle. So this total will produce your given digital output. Okay, or you can call it as capital T and Tx. The total conversion time is the sum of these two times. Okay, the equation for or the relation between these times and your voltages is T. Sometimes you can find it as TU and TD, up conversion and down conversion. T, I've just called it as T. So T into Vi by Rc equal to minus Vr by Rc into Tx. So from that, Tx equal to minus Vi by Vr into capital T. Or as I've said, you can write it like this also. Okay. In some textbook, you can find the relation like this. Okay, so this is the relation for your up and down converting times. Total time is the sum of these two times. Okay. Now the total conversion times in terms of your bits for an n bit ADC, T or C or time of conversion is 2 into 2 raised to n by t clock, or you can write it as 1 by t clock is f clock, or 2 into 2 raised to n into f clock. So this is the dual slope integrating type of ADC. These are the 4 type of ADCs that we are discussing in this video. I really hope that you found the video useful. The most important are the equations and the structures. You should be generally aware of how the overview of working of the ADCs, what are the different types and how is its general structure, what is actually happening in the ADC. You don't need the total each and every point of working for your competitive examination, but you require it for your semester examination. And for competitive examination, the most important one are the concepts and the equations. Okay, so I really hope that you found this video useful. If yes, please do give it a thumbs up and also share this video with maximum of friends. And if you want more videos, please do subscribe to the channel. The notes of this video is already been uploaded to the Facebook page of EC Electronics. You can find it over there. And I'm telling it once again, please do subscribe to the channel. Thanks for watching and keep on watching.